But did you keep track of prep? Yeah, if you keep track of prep, that's the same thing. It has the same information. Yeah. All right, the recorder is on, so I am going to get started. This is our last class meeting, the last lecture. On Thursday, we have our final exam. Okay, so we're going to go through some of the final exam candidate, practice questions. Before we go there, okay, I think in the previous class I did tell you guys that I would write the A-star algorithm, right? And I did. Okay, it took a little longer than I expected because I did not know I did not realize how how long it had been since I last programmed in Perl. So we'll take a look at this program. Just because I spent so much time on it, you have to take a look at it, right? But the thing is, you can download it too, and if you can find an environment to run Perl, you can run this program as well. You can easily change this program, quote unquote, easily change this program to run other types of algorithms, okay? Because this is an algorithm. The most difficult part of the algorithm was not the A-star algorithm. It was how to read a tree in XML format into the program. That was actually the hardest part of the entire program. So once I figured that part out, it was not too bad. Okay, so if you unzip the file, it creates a folder called A-star, and in the folder there are two files. One is graph.xml, which is an XML representation of a graph. I will show you the content of that one. And the other one is A-star.pl, which is the Perl script that is actually implementing A-star. The algorithm itself, when you look into the profile, some of the stuff may look kind of really awkward. There are a lot of curly braces and dollar signs, but for the most part, you can map it directly to the algorithm that we were following in class in Wikipedia. Graph.xml, which is the first file we'll take a quick look at, is an XML file, and that's basically what it is. It has, basically one big section, which is graph, and the graph has two sets. One set is vertices, and the other one will be edges. The set of vertices has 5 vertices in this case. The ID are the names of the individual vertices, and then the H value is the heuristic of that vertex to the goal state. Are there any questions about the representation of a vertex? And then we have the second set, which is the set of all the edges. And in that one, we have each edge has a from and a to, as well as a cost of that particular edge. So in this case, this is actually representing the very same question that we have in the practice exam. Okay, so if I pop up that particular graph, you will see that it is actually exactly the same thing. So let's go to practice final exam. So when you look at this picture, we have A, B, C, D, E as the vertices, and then when you look into the cost and also the heuristic function, it is the same thing as what we have in the XML file. So if you want to play with this, you're definitely encouraged to play with this particular graph. You can add additional edges to it, remove some from it, make certain vertices disconnected, completely, and see what happens. Okay, run the algorithm and see what happens. All right, so this is the first file which contains the actual graph itself. Are there any questions about how a graph is represented in XML? I think in general, you guys get a basic idea of how this is represented. Any questions about this one? No questions? This is all good? Okay. So if this is all good, we're going to move on to the algorithm itself, which is written in Perl. Okay. And I don't think syntax highlighting is going to help. No, that's worse, right? Okay. So the algorithm itself is done here. Okay, so from line 14, which is A-star, all the way down to the end curly brace corresponding to that one, which is all the way down here, down to line 81. That's the algorithm itself. Okay, it's a little bit long, and because I did it in Perl, certain things may look a little bit awkward if you're not used to Perl. On the other hand, I try to keep the same names as the algorithms on Wikipedia. In other words, when you look at some of the variable names, open set, closed set, G score, F score, current, came from, and also tentative G-score. All of those names are the same as in the algorithm on Wikipedia. So for the most part, if you read the code and just kind of ignore the Perl syntax part, it is really doing the same thing as the algorithm on Wikipedia. Are there any questions about this one? No? Okay. All right, so I'll just go ahead and map this algorithm to the algorithm on Wikipedia. So this way you have a clearer picture of how those two map. So A star algorithm, and switch to the tab. There we go. Okay, so this is the actual pseudocode algorithm. We have a graph. We want to indicate what is the start vertex, what is the goal vertex. In the algorithm, we have the same thing, except these two are passed as parameters. This is kind of like an awkward thing for Perl to pass parameters because it passes a list of things to a subroutine. And from that list of things, I can use the shift command to extract individual components. And basically, I'm using start, goal, and graph as the three parameters of this subroutine. You don't really have to understand Perl syntax entirely to get this to work. I'm just explaining how I got the individual parts. And then we also have the other local variables. We have came from, open set, closed set, G-score, F-score, and current. They are all local variables in this particular subroutine, and they map to the exact same names in the actual algorithm. Are there any questions about these guys? Okay, I'm not going to explain Perl syntax in this class, so don't worry too much about the percent symbol as opposed to the dollar symbol as opposed to the @ symbol. Okay, because those are specific things to Perl. But for the most part, other than not using the same open bracket, closed bracket sort of thing, you can see the initialization is kind of the same thing as in the algorithm itself, in the pseudocode. Because in the pseudocode, we want T-score of the start state or the start vertex to be 0. And that's basically accomplished by this statement here. We want F-score. Now, F-score is a little bit harder because F-score of the start vertex is the G-score of the start vertex plus the heuristic cost estimate from the start vertex to the goal vertex. In this case, I simplify so there's only one goal vertex, and that's why goal is not a part of the function, and I just have h to imply it is the heuristic value of going to the goal vertex. Is that okay so far? Okay. Does everybody understand the assumption that there's only one goal vertex, and so all the edge values are with respect to vertex E in this case? This is the difficult part to read in Perl, because this part, which is basically saying, give me an estimate of how much it will cost from the start vertex to the goal vertex, is translated into this part in the actual Perl code. The DEF, which stands for definition, is coming from the definition of a particular vertex. And within that definition, there's an H value or an H attribute, which is the heuristic value. So that's how I pull the heuristic value of a particular vertex to the destination or the final vertex from the XML file. Is that okay so far? So if you look at the structure of the code, it is actually pretty much the same thing as in the pseudocode. Line 27 is how I add something to a set. Okay, I use a hash, which is kind of like a map, and I just say, okay, map the start vertex to 1. Well, that's basically saying it is present in the set. If I remove an item from the hash, it is the same thing as removing something from a particular set. Okay, so are there any questions about these 3 lines from line 27 to line 29 of the Perl code, and correspond those 3 lines to the 3 lines in the pseudocode, which is this part of the pseudocode? Okay, are there any questions I can answer? You guys okay with that? Okay. How about you guys? Okay. All right. So the loop itself, I have changed a little bit as well because I really dislike having a return statement inside the conditional statement inside the loop. So I changed the loop condition a little bit. I still have checking for the open set being not empty to stay in the loop, and that part is done here. Okay. To cast something into a scalar is basically to return the size of something. So I'm looking up at all the keys of a hash, and if the list is non-empty, which means I have more than 0 items in the list, that means the set is non-empty. Okay, so that takes the first part. The second part is new, which is basically saying as long as the current vertex is not the goal vertex, I have to stay in the loop because I have not found the goal vertex yet. Is that part okay? Now, the highlighted portion of this code in Perl is mapping to this condition. It is negated because this is a condition to get out of the loop. It doesn't even just get out of the loop, it gets out of the entire subroutine. So when I need to specify the stay in loop condition, I have to invert it and also use a conjunction to add to, okay, as long as this open set is not empty and we are not at the goal vertex yet, stay in the loop, keep searching. Are we doing okay so far with that kind of small alteration of the code? The rest is pretty much the same. This one is also a little bit hard to read in the actual pseudocode, in the Perl code. This one is saying, okay, among all the nodes or vertices in the open set, I want to pick the one with the least f_value. That's what the original pseudocode is saying. And in the Perl code, to do this is a little bit cryptic. And it is done by this particular, it's done by this particular expression. Once again, I'm not going to explain it. You can go to any search engine and look for Perl sort, okay, to figure out how sort works in Perl. But this accomplishes the same thing. Okay, I'm picking out the element in open set that has the least f_value. Okay. But all you need to do is to understand the overall picture. Okay, which statement or which part of the expression maps to which part of the actual pseudocode on Wikipedia. Because the objective is when I run this algorithm, I want you guys to understand how it goes about getting things done. The next line, line 34, does not need a whole lot of explanation. All it does is to print out what is my current vertex. Because I want this as a part of the output, so when I run the algorithm, I can actually see from the output, okay, what is my current vertex? And assuming this is my current vertex, who are the neighbors, and who am I adding to the open set, who am I removing from the open set and putting into the closed set? So this is really just something that will generate an output, so you can actually see from the output what the algorithm is doing. Are we okay with line 34? So line 34 is not in the actual pseudocode, and I just put it here so that we can, when we run the algorithm, we can actually see what it's doing. Okay. Moving on to line 35. Line 35 is also in a little bit different from the original pseudocode. It basically says, okay, now that we have removed, now that we have extracted one vertex out of the open set, we want to see if this is the actual goal vertex. Because if it is, there's nothing to do. I have already found the shortest path to the goal vertex. If not, I got something else to do. Because if not, I'm going to say, okay, from this particular vertex, which is now called current, where do we go next? Okay, what do we want to explore next? That's why there's a condition of saying if the current vertex is not, NE stands for not equal to the goal vertex, then we perform the then statement of this conditional statement. So this part is also a little bit different from the pseudocode because what the pseudocode does is indirect. In the pseudocode, it checks for equality and then it returns from the entire subroutine. It just gets out of the entire subroutine, which implies If you continue execution with this part here, it is corresponding to the current vertex is not the goal vertex. Okay, so that's it. So instead of representing the logic this way, in the pseudocode, I chose to represent it in a slightly different way, so I would not use return inside the conditional statement, inside the loop. Is that okay so far? Okay, all right. So now we are looking at removing a particular element from a set. That part is done by this statement here. Let's see, where is it? Oh, I just got past it, which is this part here. So deleting open set in curly braces, dollar current is the way. This is how I remove quote unquote an element from a set. Okay, when a set is actually represented as what we call a hash in Perl. Is that okay? A hash is kind of like a map. Do you guys know what a map is from cisp440 or 400? I don't know which class they. With 430. 430? Okay. So it's basically the same thing as a map. I'm just mapping a particular vertex to 0 or 1. Or just 1 actually, because if I want to remove it, I just remove it from the map entirely, which is what the delete command does. Okay. And I have to add it to the closed set. This is how I add the same element to the closed set. It's basically saying, okay, I want this particular hash, or if you will, a map, to include a new element, and we want to map the current vertex to a constant value of 1. Basically just to say, okay, it's there, okay? All I want is to say it's here. Are there any questions about the program up to this point? So up to this point, we are here in the pseudocode, adding the current vertex to the closed set. So if you just kind of read the keywords, in the pseudocode and the keywords in the Perl code, you can actually make almost a one-to-one correspondence. This is another loop. Okay, this is the loop that I kind of messed up last time, because I did not go for the additional iterations. It says, for each neighbor in the neighbor set of our current vertex, we want to do the following. This is how it is expressed in pseudocode, and this is how it is expressed in Perl code. You can see that it's kind of related, but it's not exactly expressed the same way. I'm not going to explain the syntax. So once again, this statement on line 41, it states and saying the same thing. It basically says for each neighbor of the current vertex, okay, and the neighbor has a name of $n. So for each neighbor n of the current vertex, do the following. Is that okay so far? Okay. And then the rest is just printing out the which neighbor we are considering from the current vertex, and if n, which is the neighbor, is not in the closed set, then we do the following, and that is mapping exactly to this conditional statement here. So this conditional statement is kind of this conditional statement here. Nope, I take it back. It's right here. So this conditional statement is mapping to this conditional statement, but once again, it is inverted. When you look at the original pseudocode, it basically says if neighbor is in the closed set, which means we have already considered this particular vertex, continue. Continue is the same thing as continue in C and C++. What does it do to a loop?
Go to the next neighbor.
It goes to the next iteration. In other words, it goes back to reevaluate the condition of the loop. Okay, and once again, this is another way to get out of a loop, and I do not like it. So in the Perl logic, I just decided to invert it. Okay, I check for the reverse of this one, which is as long as n is not in the closed set, do the following. And the following, which is starting on line 46, the first one is to calculate tentative G-score. So this code is the same thing as this code here, to calculate the tentative G-score. Once again, the syntax is a little bit different between the Perl code and the pseudocode, but it does get the job done. Okay, most of the time that I spent last night was actually looking up the syntax of Perl and also the library calls that I need in order to parse an XML file. Those were actually much more time consuming than the algorithm itself. And then I made one really stupid mistake that I'll talk about later. And then it prints the tentative G-score of this particular node, and it's just for reporting a number. Yep, go ahead.
Yeah. Where do we define the neighbor nodes?
The neighbor nodes are implicitly defined in the XML file. So that's a good question. Let's go back to the XML file, which is graph.xml. So the neighbor is actually implied by the two part of an edge, but it's internally represented, by it's stored internally, using a hash. So for each hash of the from, it basically remembers who we connect to and how much is to connect to. And let's go back to the file. Okay, so this statement here on line 48, okay, this conditional statement is actually mapping to this conditional statement here, which is the kind of longer statement. It says, if neighbor is not in the open set, in other words, if someone has not already suggested to consider neighbor as one of the vertices to explore, or if the tentative G-score is less than G-score of neighbor, which is basically saying, okay, we have already estimated a cost going through neighbor to the destination, but the new estimate is lower, okay? So if one of these two conditions is true, we want to go through this code because we want to, first of all, add this particular vertex neighbor into the open set so that it will be considered as one of the alternatives to explore later on. And two, we also want to update the G-score of this particular vertex. So in either condition, we have to go through we have to get into the conditional statement to update one of the two things, or both of the things that we want to update. That is represented by this condition here. So the first one is basically checking membership of n in the set called open set. That's the first part. And then the second part, once again, is just checking the tentative G-score, which is based on the heuristic function of n, and G-score of n that is known up to this point. So that's basically how this part works. Are there any questions about the mapping between the pseudocode to the Perl code? No questions? Okay. All right. And inside the conditional statement, we have the same stuff here. We update came from to current. In other words, we want to remember the known shortest path to the destination from the start vertex through the neighbor is through the current vertex. That's basically what it's saying. Okay. Are there any questions about this part? Because this part is the same thing as pref. Came from in this particular pseudocode is the same thing as pref in your homework assignment. And later on, we'll take a look at how do we change this whole thing so that instead of using the A-star algorithm, we'll basically quote unquote revert back to the Dijkstra algorithm, which is your homework assignment, because these two algorithms are definitely related. The next statement in pseudocode is to update the G-score of neighbor. Okay, are there any questions that I can answer? Are there any questions that I can answer?
Is it me?
Hmm?
Are you asking me?
No. I'm asking those two. You guys okay?
Yeah.
Okay. Because if you have any questions, just go ahead and ask those questions. All right, and then the next thing we do in the pseudocode is to calculate and update the F-score, which is done by this statement in Perl. Okay. Once you read this part a little bit, you can kind of recognize the syntax because we have seen something like this before. when we computed the tentative G-score, we have done something like this already. We have already accessed the heuristic function of a particular node. And then we have this conditional statement, which is saying if neighbor is not in the open set, add it to the open set. And this is exactly what this part is saying. Okay, if the syntax is different, just because it is not. This is not pseudocode; it's actual pro code. And this is how we add neighbor n to the open set, which is the same thing as we add anything to the open set from before. And when this is all done, okay, well, there's a big, huge conditional statement here. But the else of this conditional statement is corresponding to return reconstruct path, or that particular condition. In the original pseudocode, which is what we are seeing here, it does not make any conclusion. It does not print anything when we get to the goal vertex. So in the Perl code, I specifically print that statement and say, hey, the current node is actually the goal vertex, and we can now exit the loop. Once we exit the loop, we have this part here, which is corresponding to reconstruct path. I did not write a subroutine called reconstruct path to basically construct the path from the start vertex all the way to the goal vertex. So I did not write a subroutine. Instead, what I did was to actually write the necessary code here. So the path is basically reconstructed by this particular subroutine. It is actually the same logic. This is the same logic as reconstruct. If you look at how this loop is structured, it is the same thing as how this one is structured here. So at the end of this entire Perl subroutine, it returns the path as a particular list. If no path is found, then I return an empty list. Okay, so that's an indication that we could not find a path. Are there any questions about this particular program? If you want to, you can print it out. Okay, you can print out the Perl program and bring it to the test. I don't think it's going to be very helpful because unless you can interpret Perl at the speed of the Perl interpreter, then it might be helpful. Otherwise, the pseudocode is actually much more friendly to you. Okay, but the idea of writing this program in Perl. Yep.
What version of Perl you use? I know there was a big break between I think one version and another, right? The new one.
If one thing that is really good about Perl, or one of the really good things about Perl, is backward compatibility. The newer versions of Perl have more features, but I think what I use in this particular program, they're all backward compatible. So unlike Visual Basic or PHP, where they many times they would introduce a feature, or they would actually say, oh, that was a bad idea, and they would deprecate and actually disallow features that people have been using for years. So new programs, or I should say old programs, would not actually run with a newer version of the interpreter. With Perl is the opposite. They try to make everything backward compatible. So you might complain and say, well, this is deprecated. It's not a good idea to keep doing things this way, but it will still let it run with the same meaning as before. All right. So this is the basic algorithm. The rest of this, okay, this is the part that took me the most time. From line 83 all the way to basically the end of this program. And mostly it's just from line 83 to line 102. This is the part that actually parses the XML file and store the information in the XML file into the hash variables in Perl. This took me, I would say, at least 2/3 of the time of writing this program is to figure out how to read an XML file into a Perl program, so I can actually refer to the content of the XML file. What about the other 1/3 of the time? Well, the other 1/3 of the time had to do with a bug that I put into this program. When I wrote this program, I'll show you all the relevant part here. When I wrote this program the first time, I had another my here, which turned out to be a really, really bad idea. Because when you say my something in Perl, you're declaring a local variable. It's the same thing as int current in C and C++. Yep.
Sorry, but would you be able to turn on the syntax highlighting?
I don't think that's going to be pleasant.
Oh, really?
Yeah, we tried that already.
Oh, gotcha. Yeah, you're right. Yeah, that's pretty horrible.
So this turned out to be a really bad idea because this is a local variable that is actually masking the other local variable. So the one declared on line 25 is now masked by the one on line 33. So I was wondering, why is this loop not exiting? And I checked everything in the loop. I checked the value of current. Everything is good. But how come on line 31 it is always saying current does not equal to goal is true? Well, as it turned out, I'm not using the same current because now we have a local variable current on line 33 that I used throughout the body of the loop, but it disappears at the end of the loop because it's the closing of the scope. So by the time I get to line 31, it is using the current from line 25, which was never altered or changed by the algorithm at all. So an empty string is always not going to match any particular string, and as a result, the loop refused to exit. That took up the other 2/3 of the time. This program took me from, I would say, about 10:30 to 1:40 last night.
That would explain why you weren't answering my emails.
Yes, that would certainly explain that. It's like, why is this not working? So, yeah, not a good idea.
To stay up till 1:30 doing a program? No.
1:40.
No, sorry, 1:40.
1:40.
I want to take 10 minutes away.
Okay, so now we want to see it run because remember the whole purpose of this program was not for me to practice Perl, which I really like to do, but what it really is the full intention is to go through the steps that we started in the previous class, but this time it's going to be done by the program. Okay, so it will show you how the values are all getting updated. To run this program, depending on your platform, okay, you might have to install Perl first. So if you install Perl separately, you might have to say Perl first as the command line, and then you just run A* as the command line. Oh, okay, it's complaining XML parser is not installed on this computer. Okay, fine, we'll fix that. XML parse. There we go. There we go. That's one. It will go away after today's class because it's not this part is not persistent. But it will get there.
You don't have.
I did not have. I only have home being persistent.
Not
Everything
slash
else
user.
is not.
Yeah.
For a particular reason, because if those things are also persistent, I have other issues.
Yeah.
There we go.
It's crashing.
Yep. So that's how the program runs. Okay. So it will basically just do all the printouts and let you know who is our current vertex, which neighbor of this current vertex are we considering. What is the value of, what is the tentative G-score of that particular vertex? And are we going to add it to the open set or so and so on and so forth. Now you can modify this algorithm and add more print statements if you want to get more details out of it. But this really gives you an idea of how A* works. Are we doing okay so far with that concept? So as far as the syntax is concerned, if you can print something out, that would be fine. Okay, you don't have to really understand Perl syntax. I'm not going to test you guys on Perl syntax unless you guys want to.
No.
If the majority of the class says yes, we want to be tested on Perl syntax because I'm really good at it and that will bump up my GPA, then I can throw that in. No, no, not even an extra credit question.
Extra credit.
I knew that somebody's going to say, yep, extra credit, sure. Okay, so I'm going to pipe it through less and just take a quick look at this. So what it's saying is, we'll set the current vertex to A first. Does that make any sense? Why are we setting the current vertex to A? Because that's our start vertex, exactly. That's the only thing in open set to begin with. So it has to be the first thing to be extracted out of the open set. Then it concludes, that A is not the goal. Okay, fine. Okay, that's exactly what we know about it. And it tells you that we are first considering, the neighbor C of A. Then we consider B of A, and then we consider D of A. It doesn't really tell you which one we add to the open set, and we can change that. So I'm going to show you how to alter this program in case you want to do the same thing too. So what you want to do if you want to change it is we're considering the neighbor, and every time we do something that is significant, like here, okay, we can basically indicate that we're going to update for this particular neighbor. So the way to do it is to use a print, and we simply want to say update information of vertex. And if you use the $ within the double quoted string, you can refer to the value of a particular variable. In this case, it is n. N is the name of the neighbor. And \n for end of line. So this is how we can add additional print statements, so that in the output of this program, you can actually get a better idea of what is getting updated and what are the values that we're updating. So right here, we can do the same thing, okay? So when we update everything here, I'm just adding more stuff here so that you don't have to, okay? So I can zip it up, upload it back to Moodle. So this way, when you download it, you already have all the extra print statements. So we say cisp4 open bracket, and then $n equals to tentative cisp4. And then we can also do the same thing about the f-score. And this part may be a little more tricky because I might need to refer to the dot notation, by the way, is concatenation of strings. So we are concatenating f-score, open curly brace, here we can say print add $n to open set. Okay, so I think with these additional print statements, I think it should be easier to read. So this time you can definitely see that how we are updating the G-score, F-score, and when we add something to the open set. And you can do more. Okay, if you want to print more stuff, go ahead and change the program to do more. Are there any questions about this program? Is this going to help you understand the A-star algorithm a little bit better? Because instead of following it by hand, now you have the program actually doing it and showing you the ordering of the updates. And then what you can do, okay, to study for the exam, is to change the graphs. Okay, the graph that I have included is the one in the practice test. Okay, so what you can do is to change it so you can say, okay, what if we have a cycle? What if we have a loop in the graph? Okay, see how we handle it. Okay? You can try to trick A-star algorithm. Okay, you can try to trick A-star algorithm by saying, oh, the heuristic function. Okay, I'm just going to draw this on the whiteboard. You can basically say this is my, this is one of the vertices, and you can say, oh, this is about 1, this is 1, and this is 1 as well. This is 1, 1, and 1. But from here, the h value of this particular vertex is really low, and from here, the h value is the actual cost to the final vertex. So this one is going to be h equals to 0 for this one, and h equals to some value over here. So let's say 8 over here. So the A-star algorithm will naturally favor this particular vertex because it looks the most promising, right? So you can basically see how at some point, through the graph, through the updates, it will actually figure out and say, hey, this is not going to work out, and it will actually change and start to use the other one, as it works its way to the goal, vertex. Okay, so that's how you can use this program to get a better understanding of the A-star algorithm, because you can change the XML file to represent a different graph, and you can change the graph in a way that it is quote-unquote tricky, and see how we can trick A-star to update several times and say, I thought this was the best path to the goal vertex. Whoops, that doesn't turn out to be a very good idea. And it actually knows how to quote unquote back up. It doesn't really back up, it actually picks the next best alternative and so on, but eventually it will find the shortest path. Are we doing okay so far with this? Or not? This is okay so far? Okay. All right. So before I forget, I'm gonna re-upload this zip file. I will zip it again. So zip-r, what's the name? A star. Zip. A star is the folder. So I will re-upload this into Moodle. How many people need some help with running Perl in Windows? I will get that help for you. There we go. Seriously. Yep. There we go. We have the binaries and there we go.
Source, source, recommended.
Yep. Well, but you also need to get the library, that particular library. So you need to do that as well. Any questions about this?
What's the name of the XML library that you use again?
Yeah, it's XML parser. Yeah, XML parser is the library. And if you Google for that one, you can search, you can find out how to do that too. So Perl XML parser. It's in Sipan, and everything in Sipan has instructions to download and install it. There we go. All right, so quick start. Install Sipan M to make installing other modules easier. And you can do it in Windows 32. So there you have most of the instructions. I know the font is a little small, but since it's getting recorded, you can get to it too. But that's only if you want to run it, run the program itself, which I think is a good idea. What? Okay, how many people actually need more step-by-step instructions to install Perl? Because I can run a virtual machine right now and running in Windows.
You want to, so you might as well do it.
Well, let me go through some of the other questions first. If I have time, then we'll go back and actually do this part. Or if there are people who are actually requesting it, I can post that on YouTube as well. I can do it at home and post it on YouTube. All right. So getting back to trees and the practice exam. So question number one is kind of like the output of the program that I just speak of. Okay. So you can kind of expect the question that you will get in the actual exam is not of that nature. Okay. So instead, I will ask you about construct a particular graph that has certain properties that will make the A-star algorithm behave in a certain way. So that's why it might be helpful to experiment with the A-star algorithm just to find out how it works, at least in principle. Some people do not need to run the Perl program because some people are really good at looking at pseudocode or reading pseudocode and get a general understanding of how it works. Some other people want to run it with an actual program to visualize and actually see how it works. So whichever way suits you better, that's how you want to study for this particular topic. And I think I did not finish up the upload. I did not.
You got something?
Okay, let's redo it. So now the updated profile is now uploaded. So if you want to play with it, you can download it. All right. So this question is pretty much done. And we're moving on to question number 2. Question number 2 is asking, which vertices of the graph described in question number 1 can serve as the root of a spanning tree that spans all the vertices? Okay, are there any questions about the question itself? Is there anything I can do to clarify what this question is asking? Which vertices out of A, B, C, D, E of the graph described in question number 1 can serve as the root of a spanning tree that spans all the vertices? Now remember, this is a digraph, it is directed. Go ahead.
So can you explain what a spanning tree is again, really fast?
A spanning tree is a subgraph, so you can kind of look at it as a skeletal part of a graph where the tree, all the vertices of the tree are all the vertices in the original graph. So you're using the minimum number of edges to make all the vertices connect.
Gotcha.
Any other questions about what? Is that okay? No, go ahead.
Is spanning tree different from a minimum spanning tree, or are they synonymous?
A minimum spanning tree is a spanning tree, but it has the minimum weight compared to all the alternatives, which we'll also address.
Gotcha.
Yep. Yep, go ahead.
When you say minimum number of edges, do you mean the physical number of edges or the cost of the edges?
If it's just a spanning tree, it is the number of. If it is a minimum spanning tree, then it is the summation of all the cost of the edges. All right, so question number 2 is not asking about a minimum spanning tree. It is just asking how many vertices can serve as the root of a spanning tree, okay, of all the, that will span all the vertices. In other words, I don't want a spanning forest, okay? I don't want individual trees. I want a single tree to span all of the vertices. Is that part okay? Because that really is a part of the question, because it is spelled out here. That spans all the vertices. So you have to understand what that means in order to answer this question correctly. Because otherwise, if I ask this in a different way and basically say, okay, you can consider not only spanning trees, but also spanning forests, then you have more choices. Because a spanning forest means that you can have multiple trees, and you can have trees that are basically singleton. It is really just the root, because those trees may not be connected. I think I can illustrate those concepts in just a little bit. Okay. All right. So, given what the question itself is asking, is there anything I can clarify in the question itself? Are those terms okay?
When you say spans all the vertices, it means encompasses?
It connects all the vertices.
Okay.
Yeah, spanning means connecting,
Gotcha.
but span is a kind of more specific word for trees. All right, so let's go back and take a look at the graph here. Okay, so the one spanning tree that we know for sure is a spanning tree is the one that we just constructed. Now, what do I mean by the one that we just constructed? Let's take a look. So what we'll do is we will take a look at the A-star algorithm. So we'll go ahead and run the A-star algorithm again. And we'll take a look at how we update all the vertices. So I have to run it through less because I have the page up in page now. When you look at the final output of this algorithm, it shows the shortest path from A to E. But along the way, it also shows the alternate paths to each and every single vertex. So let's keep track of all the came from, okay? All the updates of came from, we want to keep track of all of those things. So to do this, I can do that. The program did not update that, okay? Did not show that. So then I have to change the algorithm first. I'm not gonna re-zip and re-upload this. You can add this line if you want to. There we go. This makes it so much easier to read. All right. So what we'll do is we'll draw a picture of this. Okay. So we have E, and it says here E came from D. Is that okay? So this is how we draw the edge. And then earlier we have B came from, so E came from B, but that is now changed. Okay. So originally we had this edge here. But because of the second update, that edge is now gone. Okay, it is no longer represented. Is that okay so far? Because you can only have one came from for each vertex. It can only be coming from one other vertex. And then we go back in time. We say, from D comes from B. Okay, so this comes from B. And then we look a little bit more. It says here C comes from A. Now C is not here, so we'll start the other part. So we say C comes from A. Okay. And then we'll take a look at A and D are also connected. So we now have A. D comes from A. So that. And then finally we have B comes from A. Oh, but that's updated later. Okay, so this edge was later replaced by the other edge. Okay. So right now what we have is a graph that looks like this. Wait, that cannot be the case. I cannot have two things going into D. So D is
Path from A to D was replaced. I'm pretty sure the path from A to D was the one that was replaced.
If you're replacing it the same way that you were doing when you started, then that means A to B would be the current path to get to D, not A to D.
No, well, okay, let me double check. No, B going to D is the one that we kept because that's the second update.
Right, and you got rid of E to B.
This one away. So how do we get to B?
From A.
From A?
Yeah.
Okay. All right. So let me just double check. Yep. Okay. B comes from A, and that link was never updated. Yep. Okay. There we go. All right. What does that look like to you? What is the most important property of a tree as opposed to a general graph?
There's only one way to get to each vertex.
Yep, especially with a directed graph, there's only one way to get to each vertex, except for the root. Okay, the root does not have any way to get to it. Okay, does this meet that requirement?
Yes.
Meets that requirement. So it is a tree. Okay, is a linear list a tree? A linear linked list is a tree. It is deformed, but it is still considered a tree because it still meets this requirement. We have 5 vertices, right? And because each vertex can only have one and only one incoming edge, except for the root, how many vertices or how many edges should we expect out of this graph? 4, okay? So there are, these are all kind of important things to think about because these are all results of being a tree. Is this a spanning tree? Is this a spanning tree that spans all the vertices of the original graph? Yes, it does, because all of the vertices, A, B, C, D, E, are reached by this particular tree. Is that okay? What is the weight of this particular graph, of this particular tree, which is the summation of all the edges of this graph? So for that, we can take a look at the original picture. So we can just pick out the edges of the original one. So we are going from A to B, which has a cost of 5. We're going from A to C, which has a cost of 6. B to D has a cost of 10. And then E to E has a cost of 5. So the weight of this particular spanning tree is just adding all of these numbers, which is 5 plus 6, which is 11, plus 10, which is 21, plus 5, which is 26. So the weight of this entire thing is 26. Okay? So I can just say the weight of this thing is 26. Are we still doing okay so far with these concepts? Terminology, concepts, and how to get things done. Okay. So, but what is the question asking? The question is asking which vertices of the graph described in Q1 can serve as the root of a spanning tree. I don't really care whether it's the minimum spanning tree or not. I'm just saying a spanning tree. So we just dealt with one. The question is, are there other ones? Okay. So if you think about it, there are other ones, but the same root can have multiple spanning trees as well. So when you think about A being the root, are there any spanning trees that we have not considered? This is the minimum one, but are there other ones?
C, if I'm starting from C and starting from B.
Okay, all right, so let's draw that picture. So starting from A, still considering A as the root, we can go to, A can go to D as well, okay, so we can go to D. And from D, we have only one choice, we can go to E. So now we have A, D, and E basically spanned. We only have two vertices that are not spanned. The two vertices that are not spanned are B and C. One way to do this is to say, okay, A can go to B directly, A can go to C directly. Okay, that works. But there's another way to do this, right? You can also draw this as A to D to E, but then you can go to B, because B also goes to C. This is another spanning tree. So these are, so far, these are all alternative spanning trees, but only using A as a root. Are there any other alternatives that we have not considered?
Using B as a root.
Using, well, not still using A as root. Are there any other trees that we have not considered? No, I'm still using A as a root. Are there any other spanning tree using A as a root?
A to C to D to E and then E to B.
A to C, and then from C to D, and then from D to E. Then we only have B left, and B can be attached only using, there's only one way to use B here. So B can only attach here. Yep.
That tree has the same minimum value as the first tree, so
Which one?
the one we just made.
This one?
Yeah.
Well, that will make it also a minimum spanning tree.
Okay.
A minimum span, there can be multiple alternative minimum spanning tree, because if they all have the same weight, they will all be minimum. The question is any one of these lighter than what we already think is the minimum spanning tree? Well, let's do it, right? Let's add up all of these edges, the cost of the edges. A to D is 20. Well, that pretty much,
That kills that one.
yeah, well, almost, not yet, okay? We just have to add a few more to kill it. So A to B is 5, so we only need one more edge to kill it. A to C is 6, okay? Done. We don't even care about that edge, okay? Because we don't have any negative cost to the edges. The problem with a negative cost to an edge is the optimal path or the shortest path may be a cycle. Because the more iterations you go through the cycle, the lower the cost goes. Okay, which usually does not reflect any reality. From A to D is 20, so this one is easy to rule out too. D to E is 5, and we just need one more edge to kill it. B to C is 10. There we go. Okay, that kills it. Okay, so far the alternatives. This one has the same cost, so let's double check on this one. A to C is 6, C to D is 9, D to E is 5, A to B is 5 as well. So we got
10 plus 15 is 25.
10 plus 15.
15.
Okay, that's 25. That is actually lighter than this one. So now we have a lighter one. So this one is actually this one is minimum so far. using A as a root. Are there any alternatives that we have not considered?
Using A as a root. Using A as the
Only
root?
using A as a root. Now, how do we get approach this problem? We just kind of took random shots at this. So how would you systematically go about doing this? You look at every single vertex that can be coming out of A, and then you consider, okay,
See if it generates a path to E.
Yep, exactly. So that's how you approach the second question. So when you look at the second question, it says, which vertices of, well, this is not even asking a minimum. It basically just says which one can serve as a root. So, this is not even answering question number 2 because we are still using A as a root. Okay, which one can also be used as a root? I don't really care about the cost. Okay, remember we're not looking for the minimum spanning tree. We're just looking for a vertex that can serve as the root of a spanning tree. Yes, go ahead.
Can I recommend B?
Recommending B. Yes, B in fact can be the root of a spanning tree. There are multiple ways to do it. We just need one way, right? So if you start with B, it will go to C, go to E, and it goes to C directly. It also goes to A directly. We're done. Okay? Because we just need one way to span all the vertices. I'm just asking, can it be the root? Which is a lot easier than considering all the alternatives and say which one is the weakest. What else can serve as the root? C can also be, because C goes directly to A, C goes directly to D. From A, we can go to D. From D, we can go to E. We're done. Okay? One vertex definitely cannot serve as the root. E is pretty clear because it does not even have any outgoing edges. If it has no outgoing edges, there's no way it can span any other vertices in the graph. D is not much better. It is slightly better because the only vertex it connects to is E. So that's the only tree that spans going from D. The other vertices would not be reachable from D. Yep.
So like one more kind of vertex that doesn't have any edges.
Right.
You can choose any, right?
And it would not be considered. So that the breadth would be undefined.
Well, other ones can't be considered either because they can't reach the points.
Then it will still conclude, the algorithm will still conclude, it's just that there won't be any cost, there won't be any dist defined to the goal vertex. It will still be infinity, exactly. But instead of using infinity, remember we just add up all the edges and say, okay, we'll just use that as infinity. That's basically what it is. And we can play with this algorithm too. We can just disconnect everything from D and make E still the goal vertex and see what happens. The algorithm will still conclude, except in this case it will return an empty list to indicate that there's no path to the goal vertex.
If you disconnected D? You said if you disconnected D, there's no path?
If you disconnect D and also take out this edge. Yeah, you have to disconnect both this edge and this edge. Those are the only incoming edges to E. So if you take out both of these, it won't be connectable. All right, so question 2 is done. Question 3, considering alternatives of Q2, what is the spanning tree that has the least weight? So this one is a monster. I'm not going to give you something like that in the test. Because just using A as a root, we already have these alternatives. So when you look at all the other possible roots, you have a lot of alternatives. So in the test, if I want to ask you something like this, it will be something that's much more doable with the time constraint of the test.
Typically, when you have something this. So when you have a vertex labeled A through like E, you typically always use A as the root, right? Is that just convention for most of the time?
Say again?
When you have vertex A through like whatever.
Well, it depends on the question, but most of the time, that's just how I enumerate all the vertices. Okay. Any other questions? No other questions? Okay.
Please don't ask 4 on the exam.
Number 4, the solution discovered by Dijkstra's algorithm is a tree, prove it. Well, it's easy. This one is actually easy, okay? What is the property that makes a tree a tree? or one of the results of being a tree. Especially when it's a digraph. A digraph makes it easier to explain, okay? What is it? Somebody just mentioned it earlier in the class. Except for the root, there's only one. Every vertex has one single incoming edge, right? Okay, how does that map to the algorithm? How do we represent, what is the data structure of, that is used by A star?
Tree.
No, it doesn't say anything about tree. It does not say anything about tree, but if you just look at the trace of the output, one thing tells you, oh, okay, it only keeps track of one incoming edges. Which part tells you that it only keeps track of one incoming edge to every single vertex? Came from, exactly. So came from can only keep track of one incoming edge to every single vertex, except for the root. The root does not have any incoming edges. So that basically is one of the properties of being a tree. For every single vertex, except for the root, there's only one and only one incoming edge. The root has no incoming edges whatsoever. If you have a graph that fits that description, it is a tree. Okay. So that's question number 4. Question number 5.
So 4, basically our answer would be to take and make a tree out of Dijkstra's algorithm.
No, you're going to use properties of Dijkstra's algorithm. Instead of using came from, the Dijkstra's algorithm that we use in the homework assignment has prev, P-R-E-V,
right,
which serves the same purpose as came from. So you can make the same argument, just substitute prev, in place of came from.
So number 4, we just described what you described.
I think that would be, but you have to hit all the important points, which is, to state, a tree with a directed graph, a tree is one that has a single root that has no incoming edges, and everything has exactly one and only one incoming edges. And the way we keep track of prev or came from means that every single vertex has only one incoming edge that we track. So that's why, if you just look at all the prev or the came from, then we have a tree. Assuming all the vertices are connected, it becomes a tree. We can only keep track of a tree. I should say the other way to say it is with the data structure that we have, we can only keep track of trees. We cannot keep track of anything other than a tree.
Oh yeah, I just wondered. I just thought you, some reason I was expecting some sort of mathematical proof.
You can turn it into a mathematical proof.
Oh.
I can easily,
Okay.
easily say that too.
No.
Yes.
Don't
Okay.
do that on the final.
Okay. What is the opposite of saying each node other than the root only has one and only one incoming vertices? There are a few. Okay. One is saying there are no incoming edges, right? 0. So if there are 0 incoming edges, well, those will still be trees. But it won't be a solution using Dijkstra's algorithm, because the Dijkstra's algorithm touches on every single vertex. Okay, that part is guaranteed. It will find the shortest path to every single vertex. That's the property of Dijkstra's algorithm. Okay, so that means cannot be 0 incoming vertices or 0 incoming edges. The other alternative, other than 1, is 2 or more. Is that okay? So can Dijkstra's algorithm keep track of more than 1 incoming edges using the data structure that we use? The answer is no. Because prev, open bracket something, can only keep track of 1 single value. So to say that we can keep track of something other than the tree is contradicting the algorithm itself, because we can only keep track of one thing at a time, but to represent anything other than the tree, we will have to keep track of multiple things incoming at the same time. So you can use that as an argument. It's proof by contradiction. Is that okay so far? Sort of? Question number 5, moving on. Question number 5, if a graph is used to represent the amount of time to go from one intersection to another, what would each vertex represent? An edge are edges directed or undirected? Make this graph represent reality as closely as possible. Think of examples we have already discussed in class. Okay, so do you guys remember what we talked about in class regarding this kind of thing?
Google Maps.
No, not just Google Maps. We used one other example. What was it? Mythbusters?
Oh, you're talking about the UPS truck example.
Yes, the right turn versus left turn thing. Okay, so in that case, the first question is, do we want the edges directed or undirected? What do you think? We want it to be directed, okay? That part has nothing to do with right turns only or not. It only has to do with San Francisco. Because what if you have one-way streets?
Aren't most streets two-way? Aren't most streets two-way though, or?
Have you driven in downtown, even in Sacramento? A lot of streets are not in both direction. So that means we want the edges to be in one way. Now the other reason why you want these edges to be directed instead of undirected is the traffic pattern of directions can be different. Going in one direction and going to the other direction can make a big difference. Okay. Now, of course, I'm making the assumption that people have at least traveled sufficiently to understand that part. Okay. But with a class like this, I think I can reasonably make that assumption. Has anyone driven to Davis during rush hour? Has anyone driven from Davis during the same time? Is there any difference in terms of the traffic pattern? Going to Davis, which is westbound, and going to Sacramento, which is eastbound, the same stretch, okay, the causeway. The causeway is a good example because there's no other way to get out of the causeway other than crashing out of the highway onto the
Or flying.
yeah, or flying. But there's definitely a difference, right? So how do you represent going in this direction is a lot faster, but going in the opposite direction is slower? You have to make it directed so that the edges have different costs associated with them. So the first question is, it should be directed. And then the second question is, make this graph represent reality as closely as possible. Now this one is a little bit more tricky because do we want to just use one vertex to represent each intersection, or is there something more to just the location of the intersection? How do you take right turns and left turns into consideration? Think about this a little bit. I'll just draw a picture here. All right, so this is a typical four-way intersection, and assuming this is a intersection, well, even with a stop sign, it will still work, okay? So let's say you are in this vehicle. Okay, so let's say you want to go from here, and your destination is, I don't know, over here. Okay, this is another intersection, and you want to end up somewhere around here. Okay, this is the example. Is the direction of your vehicle important? In other words, if you are not going in this direction, instead your initial condition is doing this way, would that make any difference? It would, right? So that needs to be accounted for. So that means you need multiple vertices per actual physical intersection. Which lane are you in? Does that matter? Okay. If you're on Watt, and it intersects with Fair Oaks, which lane you're in makes a lot of difference, right? So let's say this is Watt Avenue, and this is Fair Oaks.
Drive to school every day.
Okay, all right, and you're going in this direction, but instead of being on the rightmost lane, you're on the leftmost lane. Would that make a difference in terms of when you actually arrive or how you drive?
When you arrive, yes.
Because if you're in the left turn lane, you cannot make a right turn anymore.
Oh, you can, but it's not a good idea.
Not suggested, right?
Yeah.
Not recommended. So now you have to take a route going like this. In other words, each vertex has to represent each possible scenario while you are at an intersection. So that would take which lane you're in into consideration, what is your heading direction into consideration. Yep.
Because if, let's say, like the intersection of Watt and Fair Oaks, if we tried to call it A, that
Right.
wouldn't actually be representative of someone turning left and going to the C intersection, for instance, or B intersection.
Yep.
Because if you, to go down Fair Oaks, this direct, well, is that?
West, east.
Eastbound. You go eastbound on Fair Oaks, from Watt, if you're in a left-hand turn lane, you have to make a U-turn.
Exactly.
Yeah.
Now, to make this point even more refined, there are 2 right turn lanes too.
Yeah.
So if you take the left of the right turn lanes, then you'll be already in position for the left turn, either on Walnut or on Eastern.
Right.
But you just hope the car who's taking the inner right turn lane does not swerve over halfway through the turn, which I've seen a lot.
Or vice versa.
Yeah, but since I'm usually faster, I'm usually okay. The other driver will go like, what? Well, you have your own lane. I have my own lane. I'm just a little faster than you are.
Got it, but.
All right, but what the answer that I'm looking for is not like, okay, all of these details, but you kind of have to justify, why you think you need one vertex to represent this and so on. So your grade is going to be based on, in this question, will be based on how well thought out it is. Okay, if you just say each intersection is a vertex, okay, you get you definitely get a score, and it will be a passing score, but not much more than that. Okay. If you indicate, oh, direction is important too, well, it's definitely at least a B. And if you take lane into consideration or some other things, then you get an A. It's just really how thought out it is to demonstrate your understanding of how to apply vertices in the graph. Yep.
So, you want us to give you an example of this? For an example
Just take a screenshot.
Say that again?
you want us to give you an example of that?
An example would be good, like just give me what a vertex looks like. So in this case, a vertex would actually include several information. It will be a tuple that includes the actual location of the intersection, the heading, and also which lane you're in. So all of those will be a part of the tuple. So your tuple, would use the parentheses, would include your actual GPS location. Okay, you can just say location. You can indicate heading direction, which way you're heading, and and lane information. Okay, that's more than sufficient. Question number 6. Question number 6 is on time complexity. We talked about this right before spring break, and the recording of that day was lost because in the evening I recorded my cisp440 over the recording. But the notes is still there. I did write the notes about it. So if the time complexity of Dijkstra's algorithm is the big O of the square of the number of vertices, if the time to solve a graph of 20 vertices is 10 milliseconds, what is the amount of time that we need to solve a graph of 40 vertices? What do you guys think? No. Okay, what is the change of, oh, it is, sorry, take it back. It is 20 vertices is 10 milliseconds, and the 40 vertices will be 40 milliseconds. Because the ratio between the problem size is 200%, but because the big O notation is indicating the amount of time is proportional to the square of the number of vertices, when you double the amount of vertices, you have to quadruple, which is 2 squared, the amount of time. Okay, is that okay? All right. Question number 7, I want you to reconstruct this tree, given the pre and post operations per vertex. There's a trick to this one, okay? You basically look at pre as open parentheses, you look at post as closed parentheses. Okay, so if you look at it that way, it is actually pretty easy to reconstruct this whole thing. Mid is kind of like a comma, okay? If you look at the mid, it's kind of like a comma. So do you guys want me to do this or not?
Actually, I don't really understand the pre-post thing. Like, can you show it? If anyone else has a
Okay.
question, I don't know.
So the pre-post thing is discussed in Be an Arborist. And this is the algorithm, DFS, depth first search. So using the depth first search, there's a do pre. Okay, let me just highlight the lines here. So there's a do pre here, and there's a mid here, and then there's a post here. So these operations will be done in a particular order given a tree. So so if you use this algorithm and you give it a tree, it will actually just do the pre, mid, and post in a particular order. The question is reversing it. It's asking you, if I know the ordering of these operations on each vertex, reverse that to become a tree.
Gotcha.
So it's basically what a hacker would do, is to look at the observable outcome and then reverse engineer and say, okay, what is the original thing that can give me the outcome like this? Question. There was a hand over here. Any questions? Is that okay so far? Yep, go ahead.
Easiest way is just to look at the pre-statement before each letter. Like, for instance, pre-A, pre-B, pre-C all happen before.
Pre is the first time you visit it.
Right.
Right.
So all those happen before a post happens.
Right.
And then the next time you see it again, you see a pre-A. which
Post
means you go
is
back.
when you're about to get back,
Yeah.
right? Okay, so let's do this one. Right there. Okay. So if you look at this and you say, okay, pre is the first time you get to a node or get to a certain vertex. So A is the first one we get to. Which one is the next one?
B.
You get to B. So does that imply there has to be an edge going to A to B?
Yes.
Well, if it's a tree and this is the way we traverse it, these two are connected. But is that the only way that we can get to B?
Currently, yes.
Well, since this is on a tree, it has to be the only one. Okay, so all of these things are important because we're basically redoing the same thing over and over again. So A goes to B, and what is the next one? Pre-D, so D is here. And then we have post-D. What does that mean?
Go back
We
to
just
B.
made a U-turn. Okay, the post means we have hit a dead end. When there's nothing else to do, we are now going back. We are making a U-turn. So from D, we make a U-turn back to B. So now we are at B again. When we're at B, we say, oh, there's nothing else to do at B, so that means B has no other, nothing else connected to it. So we get back to A, and we say mid, okay? And then the next thing we do is a pre-C. So we have a C going from A, we have A going to C. Then we have pre-E, and then we have post-E, which means we make a U-turn back to C. Now we are in C, we have a mid-C. Mid doesn't really do a whole lot, okay? You can actually know the structure of a tree without the mid, but I'm just putting those things over there as well. Now we go to F, because there's a pre-F. Post-F going back to C. Post-C, we go back to A. And post-A, which means we're done. So this is the structure of the tree that is implied by the ordering of the pre, mid, and post operations. Now, if I were to ask you, is this a unique tree that can generate that particular pattern, what would be the answer?
Yes.
And if I ask you to prove it, how would you prove it?
Yes.
Or you can just write down, I would do it exactly the way Tech did it. That's it.
I believe it is the exact same way you would say it is.
Okay, well, we have a few more. I know some of you have classes to go to. This one is an easy one. With a tree, n vertices means there are n minus 1 edges, okay? Because the root is the only one that has no incoming edges. Given a digraph has n vertices, what is the maximum number of edges it can have? The answer is n times n minus 1 times 2.
What?
N times n minus 1 times 2. Okay, the times 2 comes from a digraph because it's directed. You can go this way, you can go the other way. N times n minus 1 is because there are n vertices. And then out of each vertex, it only has n minus 1 candidates to go to because it says also in that same question, you cannot go back to yourself.
2n squared minus 1.
The n minus 1 already imply the go forward and backward already, because normally we would divide by 2. It's only 1 here.
You are correct. So I think it's just n times n minus 1.
That means the number of vertices of a digraph is a Mersenne number. It's 2n squared minus n. It's close.
Yeah. some kind of terminology question, which means, you know.
Could you be any more ambiguous?
I think I can make it a Jeopardy style, which means you get to write a question. It has to be a question related to the terminology, and I'll be grading your question based on that. That would be a new style of question. I haven't done it before, so. But it will be, okay, I'll just put it this way. It will be advantageous to print out my notes or Wikipedia pages that explain the terminologies. Like what is a path, what is a trail, and so on. Okay, so it will be useful to print that out. It is unnecessary to run Dijkstra's algorithm on a directed tree. Why?
Because you already know the path.
Because there's only one way to get to each vertex. It has to be the shortest one, right? If there's only one way, it has to be the shortest and also the longest at the same time. And the purpose of Dijkstra's algorithm is to find the shortest path to go to each and every single vertex. Well, the only way to get to each vertex is the shortest one. There's no need to run Dijkstra's algorithm. That's it. Well, yep, go ahead.
So the final exam only contains graph and tree. We don't need to review the other topics.
Is it graph and tree?
Only about graph and tree.
I might throw something into it too, you know, but not gonna be a whole lot.
To make it interesting?
I might combine, yep.
What about cryptography?
Cryptography? No, let's just say that there won't be any cryptography questions.
I've got a Fitbit to track my
Did you get the Pulse one?
Yeah, the Charge HR.
I think that's the one that tracks the
Yeah,
heart
that's
rate well.
Okay, does it track your heartbeat?